little bit important. And you probably noticed this, but like in chapter 8, we're talking about the distribution of the sample mean and the distribution of the sample proportion. And those concepts really aren't that important on their own, but they're sort of fundamental to what we're doing in chapters 9, 10, and 11. In chapter 9, we talked about how to do confidence intervals about proportions and means. And then in chapter 10, we did hypothesis testing for one proportion in comparison to just a constant proportion. So like last Thursday, we talked a little bit about how to come up with a hypothesis test. If I say that a certain proportion, a certain population proportion, is greater than half, or greater than 3/4, or greater than a quarter, or less than half, those are all hypotheses you could make about a population proportion. You can also make these claims or these hypotheses about population means, and that would be covered in section 10.3. And then chapter 11 is going to continue very much the same as chapter 10. In chapter 11, we're going to still be doing hypothesis testing. We're still talking about either proportions or means. The difference with chapter 11 is this. The difference is that in chapter 11, you can learn how to do a hypothesis test about two population proportions. So rather than making a statement saying that, oh, I think the proportion of blank is less than 1/2, you'll be able to say, I think that population A has a smaller proportion than population B. You can compare, a proportion from two different populations. Or if you have two different populations and you are concerned about the relationship between their means, if you have some quantitative variable, and you're saying, I think the mean of population A is less than or greater than the mean of population B, that would be a hypothesis test, or a hypothesis you're claiming about the mean of two different populations. And so that's what chapter 11 is doing. They're just hypothesis tests, just like chapter 10, but they're just a little bit more complicated. And so what I've given you, what I just passed out, is kind of a high-level overview of all of this stuff. Like, it's just typed up notes, because I know it's a lot to keep straight. But between chapters 10 and 11, there's 5 types of hypothesis tests that you need to be able to know for your exam. That is 1 population proportion, 1 population mean, 2 population proportions, comparing them. And then the last 2 are comparing 2 population means, but they're sort of split up. We're going to do a different hypothesis test depending if they are a dependent sample, and a different hypothesis test if it's an independent sample. So, briefly, let me label these for you. That population proportion would have been 10.2 material. The population mean would be 10.3 material. 2 population proportions would be 11.2 material. The means with dependent samples would be 11.1. This would be 11.2. That would be 11.3. So if you want to know what section of the textbook you would find these in, that's where you find them. So I have a few blurbs about the vocabulary and language of hypothesis testing. That's on the first page where it says 0 for any hypothesis test. So all those are important to know. And then I have them labeled 1, 2, 3, 4, 5 on your remaining pages in this packet, corresponding to those 5 types of hypothesis test. So you can follow that guide, and you can successfully do every hypothesis test correctly and interpret the p-values and everything else. But there's shortcuts too, and so I want you to know the shortcuts because that might be faster and easier on the exam. And the shortcuts would be in the back of this little packet that I have called How to Use the TI, And so if you want to perform a hypothesis test about 1 population mean using a data set, I'm going to have a little 12-step process where if you have your TI-84 calculator in front of you, you can follow this to perform your hypothesis test. And likewise, I have the same thing for a population proportion, and the two population means and two population proportions. That's all here, and this is something you're going to receive on your test day along with your formula booklet, right? Just like we have in the past. Okay, so that overview aside, let's briefly go through section 10.3. So if I make a claim and I say the average height of an emperor penguin is greater than 47 inches, that would be a hypothesis I'm making about a population mean. So I'm saying the average height of every emperor penguin, the whole population. So what we would determine is what's the alternative, what's the null hypothesis? Well, my alternative hypothesis is saying that mu is greater than 47. My null hypothesis is saying that mu is less than or equal to 47. Remember, your alternative is what you're seeking evidence for. Your null hypothesis is just the converse of your alternative hypothesis. So suppose we gather data by measuring the height of 20 penguins. So my sample size is 20. Out of that sample, suppose I average the heights and my sample mean is 48.6. My sample standard deviation is calculated to be 2.8. And so like before, we're going to calculate this p-value. And that is just going to be the probability that if the population mean is actually exactly 47 inches, what is the probability that we obtain 20 random measurements from that process with a specific sample mean or a more extreme sample mean, a higher sample mean, and that sort of standard deviation. Once we calculate our p-value, we're going to compare that to our chosen level of significance. And if the p-value is less than our level of significance, then we will reject the null hypothesis by stating or concluding, we do have enough evidence in terms of enough evidence in favor of our alternative hypothesis. But if your p-value is too large, then you fail to reject your null hypothesis. Again, you choose your level of significance. You choose your level of significance based on whether or not it's okay to have a type 1 error, because the level of significance is the probability of making a type 1 error. So there's a trade-off there. First, if we want to calculate our p-value, we have to say, what is going to be the standard error of the mean? Remember, this is the standard deviation of the distribution of the sample mean, at least in our case, as best we can estimate it, right? So we use the lowercase s because this is just an approximation. And we learned from chapter 8 that was the standard deviation of the underlying process divided by square root of my sample size. Then we're going to compute a test statistic, and this is going to be a lowercase t, because when we're dealing with the distribution of the sample mean, and we don't actually know for sure what the standard deviation is, that's when we have to introduce the t distribution here, where my degrees of freedom of my t distribution are just n minus 1. So that's sort of reminiscent of chapter 9 stuff. So we compute our test statistic, and then we are faced with 3 different possible scenarios depending on whether my alternative hypothesis looks like mu greater than some number or mu less than some number, or what we call a two-tail test, where we just say mu is not equal to some constant. You can interpret your p-value that we calculate. We can interpret that by taking 1 minus your p-value and multiplying by 100%. That would represent the percent confidence you should have in favor of your alternative hypothesis. And that's your percent confidence because the remaining percent, that's the probability that you'd be committing an error, type 1 error, by rejecting your null hypothesis. So we want your p-value to be low. A low p-value represents a high degree of confidence. And another way you can think about this, another way you could do this, is you could start off by constructing a confidence interval, just like we did in section 9.2. And if your cutoff, the boundary in between your null hypothesis and your alternative hypothesis, If that cutoff falls inside of the confidence interval, then you can't reject your null hypothesis. You don't have enough evidence to conclude in favor of your alternative hypothesis. But if that hypothesis cutoff falls outside of your confidence interval, then you do have enough evidence to reject your null hypothesis. All right, it's 11:30. Let's go ahead and run through these quiz solutions. It says you take a trip to Antarctica and you decide to capture and weigh 10 penguins during your stay. So this is the weight. And you're hypothesizing that the population mean of the penguins is greater than 75. So my hypothesis, my alternative hypothesis, is going to be that the population mean is greater than 75 pounds. That means like my null hypothesis would be the converse of that the population mean is less than or equal to 75 pounds. So alternative is always what we're seeking evidence for. It's what your claim is. And the null is just going to be the converse. And it's sort of the boundary, the one number that makes the difference between my alternative and my null hypothesis. That is the number 75. So I'm going to call mu naught 75 here. The first question says, is there any evidence? Is there any evidence at all in favor of my hypothesis? So, there's really two questions here. Do you have any evidence at all? And then do you have enough evidence? You can have some evidence but not have enough evidence. But if you don't have any evidence at all, then the hypothesis test is really straightforward. And so maybe what we can calculate, we don't know the population mean, but we can calculate the sample mean. So to determine, do we have any evidence at all here? Or should we just give up? We should start off by putting my data into a list. And it is, let's see, 82, 91, 87, 85, 61, 82, 94, 66, 75, and 66. So once you have all your data punched into your list, we go back to stat, we go over to one variable statistics, calculate. And I should have a sample size of 10 if I did this right. Sometimes I look over a number and I skip and I put it to 9. So it's nice to check that n equals 10 and that's what it's supposed to. Also, I always check my minimum and my maximum because sometimes you can skip just part of a number and punch in 6 instead of 61. And then you would be able to quickly tell that your minimum doesn't actually belong to your data set, or the maximum is 94, and 94 also belongs. So I just check to make sure the minimum and the maximum fit inside my data set. And if you have the right sample size and the right min and max, that's a pretty good check to make sure you got your list in your calculator correctly. I've seen students miss exam problems before just because they didn't put the numbers in the list right. But okay, this tells me that my sample mean is 78.9. So my sample mean being 78.9, that is consistent with my alternative hypothesis, right? That's greater than 75. So yes, there is some evidence. We haven't yet determined if we have enough evidence, but at least based on the sample that I picked, there's a little bit of evidence in favor of the alternative hypothesis. Now we just have to weigh how much evidence do we have, how confident should we be. And that's the point of the hypothesis test. So the shortcut here to doing this hypothesis test is we're going to, well, we already put my measurements in list 1. So we're going to go to stat, tests, and then we're going to select number 2, which is a t-test. And the reason it's a t-test is because we're going to use the t-distribution because it's a mean. So we go to stat, you go to tests, you select number 2, the t-test. We are basing this off of our data that we have in list number 1, so I'll select data. My mu naught, that is the boundary in between my alternative hypothesis and my null hypothesis. So that should be 75. Yeah, in my instructions I put type the population mean from the null hypothesis, and again, that's what I chose because my null hypothesis is saying that my mean can be less than or equal to 75. Hence, that's why I'm putting 75 in my calculator. My data is in list 1. I always leave 1 for frequency. The type of test I'm doing is, well, I'm trying to say that my alternative hypothesis has mu greater than 75. And so I'm going to highlight the little button on my calculator that says greater than mu naught because I want my alternative hypothesis to be mu greater than mu naught. So I select that and click enter. I'm going to leave the color as blue, and then I like to do the draw option because it helps me understand what's going on here. So this picture that your calculator shows, the very center with the y-axis, that represents 75. And we know that our sample mean we calculated was 78.9. So where the shaded blue region starts, that's 78.9. And this curve represents the probability distribution of the probability density of our t distribution. And what it's trying to show you is if your null hypothesis were true, this would be the distribution of your sample mean. So the probability that if your null hypothesis were true that you would get a sample like yours or more extreme than yours, that probability is represented by the shaded blue area. So that, in other words, the shaded blue area, that represents your p-value. The shaded blue area represents your p-value. And it even tells me that p is equal to 0.153 underneath the picture. And with a p-value of 0.153, remember that p-value is the probability that if you do conclude in favor of your alternative hypothesis, that would be the probability that you're making a type 1 error. That would be the probability that you were wrong to conclude in favor of your alternative hypothesis. So you actually want your p-value to be as small as possible. We always want p to be small because if you have a small p-value, that means you have a high degree of confidence in your hypothesis. So my p-value, like the calculator says, is 0.15. And since my p-value is 0.15, I'm not very good with the mouse. Let's try this thing. Then my degree of confidence should be 1 minus my p-value times 100%. So, in other words, I should be 85% confident. So when we ask the question, you know, yeah, we have some evidence that the population mean of penguin weight is more than 75. How much evidence does this sample represent? Well, that sample gives me 85% confidence that the population mean is greater than 75 pounds. But I still have a 15% chance that the population mean is still less than 75 pounds. So whether or not you want to make this conclusion and you want to publish your results and you want to tell everybody that the population mean is greater than 75 pounds, that depends on how much you're willing to tolerate a probability of you being wrong and like making a fool of yourself. So the last question says, if you tell everyone you know the population mean of penguin weight is greater than 75 pounds, what's the probability that you're wrong? Well, the probability you're wrong is 15%. That would be the p-value. Okay. Questions about question number 1? Does that make sense what we did? Okay. Question number 2 says, in a chemical engineering cohort, so basically a graduating class of chemical engineers at Texas Tech, 26 of the students are female and 14 of the students are male. So if you just say that, you know, these distributions of, you know, the sex of the students, if that is just approximately always representative of the United States as a whole, and that any particular graduating class at Texas Tech is roughly from the same distribution that you would get anywhere in the United States, then we can say we have a hypothesis that the population proportion of female chemical engineering students is greater than half. And so, is there any evidence? Well, let's calculate my sample proportion. I don't know what my population proportion is, but I can calculate my sample proportion, and that's going to be 26 out of a total 40. So 26 out of 40 is going to be 0.65. And so my sample proportion is definitely greater than half. So when I ask, is there any evidence at all, the answer is yes. There is at least some evidence that this population proportion is greater than half. If I were to calculate a sample proportion that was less than half, then I haven't really found any evidence whatsoever in favor of my hypothesis. But the fact that at least my sample proportion was greater than half, that tells me I've got some evidence. I don't know how much evidence that represents, but it's something. So the next question says, exactly how confident should you be? Well, my level of confidence, that is always going to be 1 minus my p-value times 100%. So I first have to calculate what is my p-value, and I'm going to do this in the calculator. I'm going to go to stat, and then I'm going to go over to test, and then I'm going to choose number 5 because number 5 is a 1 proportion z test. And when I'm talking about a hypothesis about a population proportion, that distribution of the sample proportion, that's roughly a normal distribution, so that's why it's a z test. And so I'm going to choose number 5 here under stat tests. So stat test 5. Well, what is p naught? P naught is going to be the boundary between my null hypothesis and my alternative hypothesis. My null hypothesis is just the converse of my alternative hypothesis. My alternative hypothesis is going to be, what am I actually seeking evidence for? What am I trying to claim here? And my claim is that the population proportion is greater than half. So the converse of that would be that the population proportion is less than or equal to half. And my p naught is going to be 0.5 because that's the boundary between my null and alternative hypotheses. So when my calculator asks me what's p naught, I'm going to put in 0.5. My x is the number of female students in my sample, which I think was 26. Yep, 26. My n is my sample size, and I was taking a sample of 40 total students. What type of alternative hypothesis do I have? I'm claiming that the proportion is greater than 0.5. So I'm going to put greater than p naught. in my calculator, and then I'll leave the color as blue, and then I want to draw it because I just like looking at the pictures. So once again, what you're looking at on your calculator right here, that middle vertical line represents 0.5. That represents your P0. Where that blue shaded region starts, that represents 0.65. So that's the boundary between your null hypothesis being correct on the left and your alternative hypothesis being correct. No, sorry. I'm getting a little bit mixed up. So I was right to say the vertical line in the middle represents 0.5. This blue curve represents the distribution of the sample proportion. And so, of course, that's centered at 0.5. Well, it's the distribution of the sample proportion if your null hypothesis were true. And so this probability, this shaded blue region, that area, represents the probability that you would get a sample like yours if the null hypothesis were actually true. And so, of course, that's your p-value. You want that p-value to be small. You want it to be such that if the null hypothesis were true, there would only be a very small probability of getting your sample, because you're trying to find evidence that the null hypothesis is false. And since that does look relatively small, and I have a p-value of 0.029, that's good news. So my p-value is 0.029. That means that my percent confidence should be 1 minus 0.029, or 97.1%. It's a pretty high degree of confidence. And what would be the probability in percent that we're wrong? Well, it would be 2.9%, because this is what the p-value means, is the probability that you would be wrong if you concluded in favor of your alternative hypothesis. Okay, any questions about the back side of your quiz? Question number 2. Okay. So I don't actually have like slides regarding the last chapter, chapter 11. But we can still talk about the important parts. And like I said, chapter 11 is going to feel so similar to chapter 10. We're just doing hypothesis tests. But I'll point out the differences. I'll point out what you're supposed to really take note of here. So again, chapter 10 was the first 2 here. And so chapter 11 would start with hypothesis tests about 2 population proportions. And here we are. This test, this type of test, is going to apply whenever you want to evaluate the validity of a claim made about a proportion regarding 2 populations. So if I make the claim that the proportion of Midland College students who live on campus is greater than the proportion of Odessa College students who live on campus, that's a claim about a proportion regarding 2 different populations. So my first population is Midland College students. My second population is Odessa College students. And I'm just trying to make a comparison between the 2. So I might call P1 my population proportion for Midland College students. And that would mean P2 would be the population proportion for Odessa College students. And so whenever you see P1 hat, that is just going to be my sample proportion for MC. And if you see P2 hat in these formulas, that's going to represent your sample proportion for Odessa College. And we're given these formulas. The first thing we need to calculate is this thing that's just called P hat. And notice it's not P1 hat, it's not P2 hat, it's just plain old P hat. So X1 and X2 are going to correspond to Odessa College and Midland College, right? So X1 in this example would be the number of Midland College students who live on campus. And N1 would be the number of Midland College students that you sampled. That would be your sample size for your survey while you were at Midland College. X2 is the number of Odessa College students that you find living on campus, where N2 is the sample size of your random sample that you take over at Odessa College. And you need that P hat because that is going to appear in the formula right below it, right there. And if you can calculate all of these things, your sample proportions, and you know your sample sizes and everything, you can calculate this Z, where the Z is what we call our test statistic. So that Z, test statistic, it's going to serve sort of the same role as the Z test statistic did back in section 10.2 when we were dealing with one population proportion. But there's just a different formula for calculating that test statistic now. Once you just employ these formulas, you plug and chug, you get that Z naught. You have to calculate your p-value. It's kind of the heart of what a hypothesis test is calculating the p-value. And there's 3 different cases. But really, there's only one big distinction that makes these important. You can have either a one-tailed test or a two-tailed test. And if it's a one-tailed test, what you're saying is, I'm making the alternative hypothesis. I'm trying to find evidence that one of my proportions is less than or greater than the other proportion. Two-tailed tests, I normally don't ever ask questions on any kind of exam about a two-tailed test, but you can still do a two-tailed test. You're just trying to say that the proportions are not equal to each other in a two-tailed test. You're not making a claim either way. You're not saying one is greater than the other. Your claim is just that they're not the same. So kind of weird. What the two-tailed test introduces is you just multiply the p-value you're going to get times 2, and that just increases your p-value, so it would decrease your confidence in your claim. But for the most part, the questions you're going to see on exams in this class are going to be one-tailed tests. And we're going to use the CDF. And since my test statistic is a Z test statistic, the CDF is going to be the standard normal distribution CDF. And notice those vertical bars represent the absolute value. So if your Z test statistic is a negative, then leave it as a negative when you plug it into the CDF. But if you get a positive test statistic, you should make it negative when you plug into the CDF. So that's what I mean by the negative absolute value of Z right there. And that is a formula that will give you your p-value. Well, like I said, most of the time we'll be using this formula. Okay. And so, of course, if you forget how to get the CDF of the standard normal, that's going to be second VARS, and then number 2 says normal CDF. Let me make up a little example. So we're actually going to use this claim. And suppose that I conduct a sample at Midland College of 40 students, and out of those 40 students, I find that 10 live on campus. And then I conduct the same survey at Odessa College, and I find 60 students to participate in my random survey. And out of those 60 students, let's say that 8 live on campus. So then I would say my P1 hat would be 10 divided by 40, which would be 0.25. And my P2 hat would be 8 divided by 60, which, I don't know, that's 8 over 60. 0.13. My plain P hat with no 1 or 2 means that I'm going to add up the x's and then divide it by the sum of my sample sizes. So that would be 18 out of 100, or 0.18, just following that formula. And then this Z0 test statistic, that's going to be a huge pain. Because that P1 hat minus P2 hat, that's going to be a numerator of 0.12, because it's 0.25 minus 0.13. And then the denominator is going to be really annoying to calculate. So let's do it. Well, actually, screw it. You guys know how to use the calculator. At least you know how to plug in numbers into formulas using your calculator. Let's do the little shortcut. And like I said, I'm going to provide this for you on your final exam and on your midterm exam. You have one left. But we're trying to perform a hypothesis test about 2 population proportions. And get out your calculator and practice this with me. But we're going to highlight tests. Well, we're going to click stat, and then tests. And then we're going to choose number 6. So we go to stat, you go over to tests, and then we choose number 6 because it says this is going to be a 2 proportion Z test. So it's a Z test because my test statistic is a little z, and we're going to use the standard normal distribution. And we're talking about 2 proportions, and so that's why I'm choosing number 6. X1, well, that was back here. X1 is 10, N1 is 40, X2 is 8. And N2 was 60. What type of alternative hypothesis am I trying to claim? Well, I'm trying to claim that proportion of MC students who live on campus is greater than the proportion of OC students who live on campus. So I'm trying to make the alternative hypothesis that P1 is greater than P2. That is my alternative hypothesis over here, P1 greater than P2. So when my calculator is asking me P1 not equal to P2, or P1 less than P2, or P1 greater than P2, we're talking about a claim where P1 is greater than P2. So I'm going to pick P1 greater than P2, all the way on the right here. And then I'm going to go down to draw. So this is a little bit more difficult to interpret than before. But that vertical line in the middle of this picture represents a difference in your proportions of 0. Like, what if the difference between these 2 populations is actually 0? Then this blue curve represents the probability density distribution of the difference in the population proportions. Where that shaded blue region starts, that is representative of the difference that we found, the difference of 0.18. And that shaded blue region represents the probability that if the null hypothesis were true, and these two population proportions are actually equal to each other, what would be the probability that just out of the random variation that comes from random sampling that you would get a sample like yours? So the more extreme your sample is, the smaller that probability is going to be. So you'll have a smaller blue area. And we want that area to be as small as possible because that is my p-value. So we have a small blue area. We have a relatively small p-value of 0.07. And that's good because your p-value is the probability of making a type 1 error when we conclude in favor of our alternative hypothesis. So in our example, we have a p-value of 0.07, and that means my percent confidence is going to be 93%. So you can say you have 93% confidence that the population proportion of Midland College students who live on campus is greater than the population proportion of OC students who live on campus. In other words, we have 93% confidence in favor of my claim, in favor of my alternative hypothesis. And so, again, depending on the threshold you set, depending on your level of significance that you've determined, you may or may not want to publish this result, depending on whether or not it's okay for you to make a mistake, right? If it's okay for you to make a mistake, then yeah, 93% confidence is good. But if you're going to get, shamed out of your profession for making a mistake, then maybe you don't want to publish this conclusion because there's not enough evidence here. Depends on the sort of level of risk you're willing to tolerate. Okay, so the next one, number 4, this would correspond to section 11.2 in your text. This is a hypothesis test about two population means, and the important operative vocabulary word here is dependent samples. So whenever we were talking about dependent samples, this is a situation where it's like, I don't know, I have two good examples in mind. One is if you are a drug company that's trying to test the safety and effectiveness of your drug, it's really nice to have identical twins. So if you happen to be one of an identical twin, you can probably make a lot of money by volunteering for drug studies because they really, really love to have identical twins. Why do they love to have identical twins? It's because they can give one of you the drug and they can give the other one a placebo. And if there's any difference in side effects, or if there's any difference in the effectiveness of the drug at treating whatever the underlying condition is, then they can be pretty sure that that difference came from the difference in the treatment, whether or not you received a placebo or their drug. But if you just take two random people off the street and then you give one of them a placebo and one of them actually receives the drug, well, then they have different genetics, they have different lifestyles and everything else. Maybe one of them gets a rash, but that's not necessarily because they were receiving the medication. That's just because they were genetically prone to getting rashes. With twins, you are sort of controlling for genetic differences. And so if you are a drug company and you collect a bunch of sets of twins, right? So this is twin set 1, and you have an A and a B twin, and you have a twins 2, and you have an A and a B twin, and you have a twins 3, and you have an A and a B twin. And then what you do is we say, well, this group, half of the sets of twins, this is going to be my control group who receives a placebo. And then this group, this is going to be my experimental group who actually gets the real drug. this is going to be called dependent data because all of my measurements come in a measurement pair. And it's important that whenever you're analyzing the data that you don't break the pairing. Right? You don't want to accidentally compare like that twin with that twin. That wouldn't make as much sense as if you compare, you know, the one they belong with, or are actually identical. And so whenever you have some sort of measured data and you're collecting data in pairs like this, where it's dependent data, we're actually going to take, you know, let me just come up with some numbers here. This is going to be like 9, 7, 13, and this one's going to be like 5, 4, 3. We're actually going to calculate the differences. We're going to do 9 minus 5, and then we'll do 7 minus 4, and we'll do 13 minus 3, and we'll get these differences as being like, in each pair we just find the difference between the two. And then we're actually going to do just a one population, you know, mean hypothesis test, but we're going to do it on the differences of these data. And we're going to see, you know, are the differences different from 0, or are the differences, you know, the same as 0? It's basically the idea. Another good example that I've seen somewhere, I don't remember where I saw it, but like if you were trying a new acne cream and you wanted to collect evidence that it was safe and that it was effective, what you could do is you could give every participant who signs up for your trial, you could give them 1 can of just unmedicated lotion and 1 can of actual like acne treatment medicine, and have them always apply this one to the left side of their face and this one to the right side of their face every single day. And then after a month, you can look and see, does the left side have more pimples than the right side, or less pimples, or whatever. You can compare sides of your face. And since it's the same person, every other effect is already controlled for, right? Like where they go, what they eat, what their genetics are, that's all already controlled for if you just compare the sides of the same person's face. And so that's a neat example. But that would be dependent data. Independent data just means not dependent, right? And so with independent data, you're going to take 2 samples from 2 samples from 2 populations. Let me try that again. And you're actually allowed to have different sample size. You're allowed to have your first sample size not even equal to your second sample size. So just in like my example with the Odessa College students and the Midland College students, and I took a larger sample of the Odessa College students, that didn't really matter. You can still analyze your data. So anyways, in this little guide, we've got number 4, page number 4, about 2 population means from dependent samples. My example that I gave here, it says, in identical twins with seasonal allergies, treating the allergies with Zyrtec is more effective in reducing perceived symptom severity than placebo, right? So collect 30 identical twins. One of each twin gets a Zyrtec, one of each twin gets a sugar pill that looks exactly like a Zyrtec. And then after a week, you have them rate their symptom severity of their seasonal allergies. And you can then take the difference between those ratings. So step 1 is always to write your alternative and your null hypothesis in mathematical terms. So you might have the hypothesis that mu1 is less than mu2, for example. And your alternative hypothesis might look something like the converse of that. And then, like I said, for each matched pair of data, you're going to find the difference. Just subtract the 2. You need to be consistent about the way you subtract the two, so don't switch your order of subtraction as you're going down the list. Make sure you always take one set minus the other. Like do the drug measurement minus the placebo measurement, and don't ever mix up the two, or vice versa. It works either way, but you just have to be consistent. Then you're going to calculate the average difference, and so we're going to call that d bar. We're going to put a bar above it to represent the sample mean, and d stands for the difference. So the average difference is d bar. Calculate the standard deviation of the difference, and so that standard deviation is going to be lowercase s, subscript d. So this is consistent with the notation we've been using before. And then our test statistic is going to be a t-test statistic. And this should look really familiar because that's the same way we calculated the test statistic in section 10.3 with just one sample mean, except now we're doing the one population mean hypothesis test on the difference between the two. So then we calculate the p-value, very important. It's either a one-tailed test or a two-tailed test, depending on what type of claim you're making and the alternative hypothesis. And this is what we're going to use most of the time, where the CDF now is going to be the t-distribution CDF with n-1 degrees of freedom. So there's a shortcut for this on your calculator. And the shortcut is you can, I believe, let me look for it, stat tests. I want to say that two sample t-test sounds right. No, that does not, that's not right. Sorry, we're going to use two sample t-test for when we have independent samples for the very last section that we're about to talk about. Let me see if there's any shortcut at all on your calculator. If we have a hypothesis test about two population means with dependent samples, then you still have to by hand find that difference. There's no way around it. You do have to be conscious about your order of subtraction. Then you're going to put the differences in your calculator under list 1. Then you're going to just use the number 2 t-test like we did before. And last thing, on the last page here, our last type of hypothesis test is if you're talking about two population means from independent samples, they're not twins, they're not two sides of the same person's face, they have nothing to do with each other, then this is what you need. So let's say we make a claim like, I say Midland College students on average spend more money on lunch than Odessa College students. So that's like saying mu1 is greater than mu2. Well, not every Midland College student has an identical twin that goes to Odessa College. So I can't really pair people up like in the dependent case. And in fact, we can calculate a test statistic, t, using the sample means. Remember, x1 bar would be the sample mean of the amount of money that Midland College students. So if I take a random sample and I ask you how much are you spending on lunch, then we average all those numbers together, that'd be x1 bar. x2 bar is the same thing, but for Odessa College. And then I can also calculate sample standard deviations for Midland College and Odessa College, and then I'll have a different sample size for both. And after you calculate that test statistic, then we just calculate the p-value using that formula, where that CDF is the t-distribution CDF. And there is a shortcut on your calculator for this. We use number 4 in this case, where we have a 2-sample t-test. This is when it's actually appropriate to use that, number 4. when you have independent samples. So you can either punch in your data in list number 1 and list number 2. So you would go to stat and then you would go to edit. And list number 1 is going to be your data for like your Midland College students. So like somebody spends $5 on lunch, someone spends $7 on lunch, and so on for Midland College. And then once you're done with that, you jump over to list 2. This is where you put your Odessa College students' data. So you can put like, you know, something like this in. And it's okay that I have different sample sizes. I'll still go to stat, and I'll go to 2 sample t-test number 4. I'm going to say that I'm using the data that I put in list 1 and list 2. I put in 1, 1 for the frequency. Then where it says mu1, this is asking what kind of hypothesis do I have? Well, my hypothesis is going to be that, let's say, Midland College students spend less money on average than Odessa College students, so we're going to choose mu1 less than mu2. Select that one. When it asks you pooled, just say no. Pooled, no. And then we go down to draw. Again, when it draws it, the shaded blue region is going to be my p-value, representing the p-value. We want that p-value to be small if we want to conclude in favor of our alternative hypothesis. In this case, my p-value is 0.145. So that tells you, if you go around telling everybody that what you've claimed is true, that your hypothesis was correct, there's actually a 14.5% chance that you're wrong, that you're committing a type 1 error. Conversely, you could say that you are 85.5% confident that your hypothesis is correct, that your alternative hypothesis is correct. So in practice, whenever you're doing this on an exam, the 2 important skills to have is know where to find these shortcuts, which, just be confident and not afraid at all to pick up this little packet that says how to use your TI-84 and flip to the back page. The hypothesis test will be the last thing on this little how to use your TI-84 packet. Understand when you're looking at an independent sample versus a dependent sample for these 2 population mean tests. And then be able to interpret your result, right? Whenever you calculate your p-value, make sure you know how that relates to your % confidence.